And our next category is binomial distribution. This is a fascinating idea. It looks at what we were talking about before. If you flip a coin 500 times, what are your chances of getting exactly 250 out of the 500 to be heads? It's not the same as if you flip the coin 2 times. Your chances of getting 1 out of the 2 times heads happens way more often than if you took it 500 times and tried to get 250 exactly, just by the sheer amount of times that you're rolling it. So binomial distribution is a special type of experiment where there are 2 results, like flipping a coin that can get heads or tails, or doing a multiple choice test where you can get something right or something wrong. And so we have one thing we call a success. It's what we're looking for. Another thing we're looking is called a failure. So on a multiple choice question, getting it right would be your success. You got a 1 in 4 chance most often with that. And your failure would be 3 out of 4 chances because there's 3 choices. Or unless you get into those biology multiple choice questions where it goes from A to F or something like that. And you're like, really? I hate those multiple choice questions. Do you ever get those ones where, first of all, they have A, B, C, and D. And then E is A and B only. And then it's like, are you really? I know that A is right, but I'm not quite sure about B. And so you end up getting 0 on it anyways, because it's a nasty multiple choice question. Anyway, so we have a success and a failure. And whenever you're looking for a particular event, everything else would be the failure. So this comes up quite a bit as far as probabilities go. So some of the properties we talked about already. We have a certain amount of trials, like flipping a coin 500 times, or doing a multiple choice test with 40 questions. On each trial, there are only 2 possible outcomes, a success and a failure. And each one is independent. So we're not going to have a multiple choice question where you have 4 options, 3 of them are right and 1 is wrong in one choice. And the next one, 2 are right and 2 are wrong. It'd be kind of nice if the teacher did that every once in a while. But you would be like sitting there forever going, I know it's either B or C. They're both right. I don't know which one to circle. That would take a long time. And the teacher says, yeah, they're both right. That's good. Get a multiple choice question, all the answers are right. Multiple choice question where you only have 1 pick. I don't know. Anyways, so the probability P is going to be always the same, and the probability of not P, which we say use the letter Q for, is always the same. And so we have a binomial distribution. We get some new notation here. X is binomial distributed with n number of trials, and P as a probability of success. And it's a really simple formula. Does that not look simple? You have seen this formula before. Now that's the thing. Now you have to go back into your grade 12 pre-calculus and try and think, where have I seen this formula before? And I'll give you a hint. I'll give you a hint. You might not remember this notation, either because you've never seen it. That's usually means one reason you don't remember it. Or it was just shown to you in passing. But this notation with the N and the R in brackets like that, this means the same as NCR. N choose R. So now, where have you seen that NCR before? Combinations, permutations. In fact, your binomial expansion, when you were expanding A plus B to the N, was that formula. So what do we have here? We have that same idea. We have These are just written in different order. But a to the n minus k and b to the k, it's all right there. It's the same formula. It's the same idea. Why is it the same idea? Well, if you had a multiple choice test of just 3 questions, right? You either get it right or wrong, 1 and 4 for your first, 3 and 4 for your next one. And after that, it's either right or wrong, 1 and 4, 3 and 4, 1 and 4, 3 and 4. And then again, the third time, right or wrong, right or wrong, right or wrong, and right or wrong. 1 and 4, 3 and 4, 1 and 4, 3 and 4, 1 and 4, 3 and 4, 1 and 4, 3 and 4. Okay? Can you see why if we try to do that tree diagram for flipping a coin 500 times, it might get a little tedious? So we need to start recognizing some things. Now, what we're trying to figure out is a probability of x equaling something. So what if we're saying, what are my chances of getting 2 right? What is my probability if we define x in our probability distribution to be the event that you get something right, what is the probability you get exactly 2 right if you guessed on all 3 questions? Well, according to your tree diagram, you could just look and say, how many places can I get exactly 2 right? I can get 2 right this way. I can get 2 right this way. And I can get 2 right this way. So what is my probability? Well, I would add up each of those 3 branches, right? And an interesting thing happens in each of those 3 branches. Because everything is independent, can you see that you have 1/4 twice and 3/4 once in each of them? And so we would just need to multiply this by 3 in order to figure out the probability. Well, that's what our formula is saying. Our formula is saying P, this is our P right here, the probability of us getting that right is going to be 1/4. If we want it exactly 2 times, we need that 1/4 twice. And this is our Q, which is not P, which is getting it wrong. Our probability of getting it wrong is 3/4. And Q is always 1 minus P. So how is this first number 3 choose 2? Why is it that way? Well, if you were doing 3 questions and you needed to get 2 right and 1 wrong, that's the same as the number of arrangements of right, right, wrong, which you might remember from last year saying, oh, if it's 3 letters, it'd be 3 factorial, but because the 2 are repeated, we divide by 2 factorial. That will give us 3 as an answer. It's also the same as 3 choose 2, because you have 3 spaces, and you need to choose which of those 3 spaces you're going to put the correct answers in. Either 1 and 2, 1 and 3, or 2 and 3. And so that's what 3 choose 2 does. It determines where are your correct answers going to come. And then if we look at all those possibilities, it'll tell us all the cases. In this case, there's 3 of them. There's 3 cases where we have that happen. And that's what this formula does. And it saves us the work of drawing a huge tree diagram every single time. Because if we drew that huge tree diagram, we would find out this part is always the same in the branches that work out. We have 2 right and 1 wrong. So we're going to have 1/4 twice and 3/4 once, multiplied together. How many cases do we have? This one we have 3. If that multiple choice question test was 40 questions long, Well, all of a sudden you don't want to draw your tree diagram. Because 40 questions long, the end of your tree diagram might take, who knows, hundreds of pages of paper. So now you have 40 questions. You say, I wonder, what are my chances of passing perfectly if I get exactly 20 right? Well, you do 40, choose 20. So I'm going to start using the IB notation here. You would multiply that by your 1/4 chance of getting it right. That would have to happen 20 times. And you would have to get 20 of them wrong. You would type this into your calculator. You get, I'm going to just do some mental math. It's going to be close to nothing. It's going to be a very, very small number. Your chances of passing, if you guessed, are not very good, especially, or not just passing. This isn't just passing. This is getting exactly 20 out of 40. If we multiply this out, 1/4 to the power 20 is a very small number. That is very small. I was trying to do some mental math and got too small. And 3/4 out to the power 20 is also very, very small. And even though 40 choose 20 is a big number, the big number in front multiplied by the two very small numbers, the very small numbers are very, very more small than the very big number. I don't know if that makes sense. And so you end up with very small. And there's a lot of mathematics that looks like this. You know, big number times small number, is that equal to big number, is that equal to small number? And when we take calculus, sometimes look at things like, well, if I take infinity and times it by 0, what should I get? Well, you say anything times 0 is 0. Well, anything times infinity is infinity. So sometimes 0 times infinity is infinity, and sometimes 0 times infinity is 0. Just depends which is bigger or littler at the time. Yeah, sorry. Okay. All right. Take a 10-second pause for people to pick up their brains. So our formula becomes very nice. So here we've got, and it's highlighted there, a binomial distribution. Here's the notation that 6 means that there's 6 trials, and the 0.4 means that your probability of success is 40%. So if you did 6 trials and the probability of success was 40%, you could calculate the probability that x equals any number, right? In 6 trials, you could have none of your thing happen. You could have no success whatsoever. You could have 1 success, 2 successes, 3 successes, 4 successes, 5 successes, or 6 successes. In fact, we could, for this 6 trials, write out our probability distribution chart. One, 2, 3, 4, 5, 6. Oh, I forgot the 0. I knew I needed that. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3. There we go. So if you did an experiment and did that experiment 6 times, or you did a multiple choice test with 6 questions, and you guessed every single time, these are the results you could get. You could get 0 on that test. You could get 1 right, 2 right, 3 right, 4 right, 5 right, or 6 right. So with 6 trials, there will be 7 possibilities that could happen. And the probability of each one could be calculated with that formula. So if you wanted to find the probability that you would get none of them right, you'd plug in 0 for r, right? These are the number of ones that are right. These are the number of ones that are wrong. So you would have 0 of them right and all 6 of them wrong. And here you'd have 6 choose 0. If you wanted to know what are my chances of getting one of them right, be 6 choose 1, 0.4 to the 1, and then 0.6 to the 5, and so on. And so what I have here is just an example. If you wanted to say another multiple choice question where there is 5 questions, and now your chances of getting it right are 0.6. What's the probability you get exactly 4 right? We'd go 5 choose 4, 0.6 to the power 4, and 0.4 to the power 1. So I find it helpful if we think of sort of multiple choice kind of questions because it puts it in some sort of context and plug it in. Now, we can figure out all of these things. Your calculator has a built-in program to figure these things out quickly. So that built-in program is Binomial PDF. To find it, go to second vars, because above vars is distributions. And it's a hard one to find, because if you go there, it doesn't show up on your initial screen. You've got to go all the way down. I think it's to the letter A. Yes. And depending on your version of calculator, if you have the newest version of calculator, this screen comes up. If you have an older version of calculator, you'll see what I put in the notes. It'll just say Binomial PDF, and you have to know what to put in. So the newer version is really nice, because if we had 5 trials and a probability of success of 0.6, and we wanted to find out what the probability of getting exactly 4 would be, you go down to the paste, and it types everything in the right order for you. So you don't have to memorize that it's trials first, probability second, and how many exactly I want to find third. But if you have the older calculator, you do need to know what order to put it in. So you got a little bit more studying to do. Pushing enter on this gives us that 0.259 immediately. If we go to our calculator and do this again, and you leave the x value blank, and then go paste, so now it doesn't have the comma 4 at the end, it will fill in your entire probability distribution chart for you. Here's the first one, here's the second one, the third one, the fourth one. Hit the arrow over. You can see the fifth one and the sixth one, from going from 0 to 1 to 2 to 3 to 4 to 5 to 6. And one thing I like to do sometimes, if I want my probability distribution chart for something like this, if you hit your store button and then go second list 1, it'll store that data into your statistics. I actually like to store it into list 2. I'm going to show you that again. I'm going to store it now into list 2. So now I've stored it in list 1 and list 2. And if I go to my stat button and go to edit, those numbers are there, both in list 1 and list 2. In list 1, I might want to change this to 0, 1, 2, 3, 4, 5. And now I've created my probability distribution chart in my graphing calculator for myself. So now I know if I had a multiple choice test with 5 questions, and I guessed on each one, but it was a very nice multiple choice test where if you guessed, your chances of getting it right were 60%. That is very nice. So then I would find out that there's only a 1% chance that I'll get 0 on that test. There is an 8% chance I'll get 1 right, a 23% chance that I'll get 2 out of 5, a 35% chance that I'll get 3 out of 5, and there's an 8% chance I'll get 100%. Yes? Yeah. What's that? So how did I get this chart to show? I went to my Stat button, and I went to Edit. And since I stored things in List 2, those numbers appeared. So the way that we store them is after they've been calculated. So I'll calculate them again. I'll just go back up to here. So you typed in binom PDF of 5 and the 0.6, and you left the x value blank. When you do that, it calculates all of them. And then from there, right above your on button is the store button. And you hit store. It says, take my answer and store it. And then I said, store it in list 2. So I went, oops, ELF, second, number 2. So store that answer in list 2. When I push enter, it automatically puts it in there. So just for fun, I'm going to do that 40 multiple choice question test. I'm going to look at my probability of success being a normal multiple choice question test, 1 out of 4. I'm not going to put a value in for x. I'm just going to paste it to get them all. It's going to produce 41 answers for me. That's pretty crazy. Calculated all of those formulas that quickly, and now I'm going to store that into list 2. So now all 40 of those are going to get stored into list 2. When I go to stat and edit, here I could, there's a way to put numbers from 1 to 40 in really quickly. But there'd be 10, 11, 12, 13, 14, 15, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We've got a decimal 0, 0, 0, 4. Yes, decimal 0004 chance of getting exactly 50% on that question. So when I said 0 before, that's pretty close, because it's a 0.04% chance, which isn't very good. Your best chance is what you would expect, right? Your highest probability is 10 out of 40, because that would be what you would expect. If you've got a 1 and a 4 and you guess on every one, theoretically you should get 10 out of 40. But 10 out of 40 itself, there's only a 14% chance of that. There's a 13% chance you'll get 11, an 11% chance you'll get 12 right. And you can see all these probabilities spread out. And if you would add them all up, they'll add up to 100%. Your chances of getting 100% on this one, if we would go all the way down to the bottom, is less than winning a lottery. So it's very, very unlikely. So we can store our lists. We can find out all of those things quickly. That being said, you say, well, do I need to know how to use my formula? Yes. So there'll be some exam questions that take a number out in the middle or something like that where you have to know how the formula works and how to apply it. And that formula is on your formula sheet. So it's there available for you, but you have to know what things mean and how to solve for them. All right, we still got 5 minutes. We'll go. All right. So we'll end with this question. A manufacturer finds that 30% of the items produced from one of the assembly lines are defective. During a floor inspection, the manufacturer selects 6 items from this assembly line, and we want to find the probability that there's 2 defective. So one of the first things that is you're going to develop for these types of questions is recognizing them as binomial distribution. We have a success and a failure, and we have a certain number of trials. And you've done some binomial distributions already in the first part of probability without knowing it, because we could make a tree diagram and it wasn't that hard to figure out, because we didn't have many trials. You pulled marbles out twice. It could have been done as a binomial distribution, but because the tree diagram was so easy, you wouldn't have to worry about it. But here the tree diagram would be long because there would be 6 different trials done. So here we want to find the probability that x is equal to 2, because we want exactly 2 defective. We know our probability of getting a defective one is 30%. Should have paused it. All right. Okay. So using the formula, if we want 2 defective, the defective has to happen twice. The not defective one has to happen 4 times. And the 6 choose 2 in front will calculate how many times that happened in your tree diagram. Putting all those things together, you'll get approximately 0.324 correct to 3 significant figures. If you wanted to use your formula, you could have done binom PDF. You had 6 trials, probability of success is 0.3, and you want to find the number when it was 2. You could also left that 2 out and found out all 7 of them, and then said, okay, the first one's 0, the second one's 1, the third one would be 2. And you would get that same number from there. Now I'm going to introduce you to a new button on your calculator, because it says, what is the probability that at least 2 are defective? And the way that we would do that is we could figure out the probability of none of them being defective, the probability of one of them being defective, and subtract that from 1. Does that make sense? Because that would be quicker than calculating 2 defective, 3 defective, 4 defective, 5 defective, and 6 defective. 5 different cases and adding them up. It's quicker to do the opposite. Well, there is a program built into your calculator. So this would be how you would use it with the formulas. But right under binomial PDF, in the PDF's probability distribution function, there is a binom CDF, which is a cumulative distribution function. And what it does is it adds up everything in your probability distribution chart. So what this means here is if I have my probability distribution chart, just draw a picture of my probability distribution chart. X, probability x equals x. 0, 1, 2, 3, 4, 5, 6. You'd have 7 things. What your binom PDF does, especially when you leave it blank, is it tells you all 7 of these answers. What binom CDF does is it adds things up. So it will, binom CDF at the 1, will add those 2 up. If you did binom CDF and you put a 5 at the end, it would add up all 5 of them. And so if you do that calculation, you have a 58% chance of getting at least 2 defective.